Okay, let's talk about Chapter 2 in Romans, data acquisition. These are the objectives that I've identified for us, and I'll be going through real closely in the textbook, so if you didn't print off the PowerPoint slides, that's just fine. I would highly encourage that you just follow along in the textbook, because I'll be pointing out some really important stuff, and largely what we're talking about is these key concepts. I pull a lot of my exam questions from the key concept box because they do a really great job of distilling down the what's significant. It's helpful to read through the textbook still because she explains why it's so important, right? But we're going to be identifying the parts of the CT scanner and the hardware. And then we're going to discuss these different scanner generations and why they're important, why we needed to know the brief history of kind of hardware development. Then we're going to learn how to zero a CT scan table, because I know that I think especially the nuke med folks, y'all are going out possibly to clinical sites starting what, yesterday, today? Okay, cool. That's one of the very first things she doesn't talk about. She talks about referencing the table. I've always referred to it as zeroing the table. But it's one of the first things you can learn, how to zero the table, what are the areas of anatomy we need to be lining up to. It'll be different a little bit for each facility, but I've worked at a bunch of different places, and zeroing the table. We'll also talk about some concerns related to it, like legit concerns for increasing patient dose if we don't zero appropriately. Like, even though it's one of the most basic things that we do, doing it well is important. And then will all in your groups have an opportunity, final objective, to perform a CT scan today. That's one of the big things I'm driving at, is that we're all going to have an opportunity to come up to this podium and work with a CT scanner. So here is the CT scanner, and these are the parts that we are going to be thinking about. We've already talked quite a bit about slip rings. They are cool. They were developed by NASA to allow for the continuous powering of rocket engines even while they're being disengaged, right? So that technology was then put into a lot of different industries, and CT picked up on it pretty quickly with the development of the third generation scanners as a way to continuously power the gantry during data acquisition. Prior to the slip ring technology, we had to scan and then reset the scanner and then scan, and it was very laborious, and it created a bigger time gap for data acquisition and made for a number of problems. So we like slip rings. They're important to think about, and largely, again, what they're going to allow us to do is continuously have power going through the x-ray tube. So we need a generator on board. So top of page 16 in our textbook, it talks about how the generators produce a high voltage and transmit it to the x-ray tube. That's basically what the generators do. You want to be very careful around this thing. You don't need to be drinking like your giant big gulp around it, because it does have a very powerful generator inside the room. The power capacity of the generator is generally talked about in kilowatts, and this is important because the diagnostic range of energies is in the kilovolt range or kVp range. When we're talking about therapeutic energy ranges or energy ranges related to gamma radiation, sometimes we get up into the mega electron volt range, and that's quite a bit more, right? So that's not what we're playing with for us. We're using kilowatts to produce kVp. Then it will have some kind of cooling system, and it's typically fans. And that's what we have on this CT scanner here. You can see there's a bank of fans. I'll try to indicate them right in here. And they're around the detectors, but we'll have other fans in other places doing a lot of cooling. And you'll hear those fans the minute you step into a CT room, just trying to cool off all the electronics, as well as the generators and the x-ray tubes and things like that. But sometimes there's also things like oil that is helping cool certain parts of the x-ray tube. You don't need to know all the ins and outs of how the cooling system works. Just understand that it has a pretty important cooling system, and it has an important role in x-ray production. One thing that is important is thinking about these x-ray sources. And so at the bottom of page 16, she talks about the anode heat capacity in millions heat units, MHU, and the maximum anode heat dissipation rate of 1,000 heat units, KHU. These specifications are crucial if you're ever in a point where you're comparing different CT scanning systems. They determine the life of the tube. They determine how quickly the imaging can occur. They determine what kinds of energy ranges you can work with. So if you're ever in a management position and you're tasked with acquiring a CT scanner, know that the anode heat unit rating is really, really important. And it has specifically it tells us just how rugged is this scanner. How rough and tumble is it? Is it something that's going to be a good workhorse for my hospital and get a lot of work done? Or is it like a fancy kind of high-end CT scanner that I'm going to have to replace the tube on every 6 months or something? Moving along to filtration, the part that I think is important here is that filtration is going to allow us to create a more uniform range of diagnostic energies, so it's going to get rid of those weak energy ranges. And if you look at the bottom of that first paragraph on filtration, it talks about creating a more uniform beam intensity, so it will improve the image by reducing the artifacts that result from beam hardening. Okay? And the box is helpful too, in that it talks about filtration is going to reduce patient dose and increase image quality. Now, that is what we would call maybe a discussion of inherent filtration. Sometimes we talk about added filtration, and a good example of that is the bow tie filter. Okay? So sometimes we have filters that we add to certain scan protocols, and the bow tie is a good example of one. And the way that I think about the bow tie filter, y'all remember I had it on that little box, right? So we had a little box that we used when we built the CT scanner. It had a little bow tie stuck to the top of it. Is parts of the human body are basically like a hot dog, right? So for example, everyone pretty much has hot dog heads, right? Our heads are more or less tubular shaped. They're more or less basketball shaped, right? So as the scanner is spinning around and around this basketball shape, if we increase filtration out on the edges and decrease filtration towards the center and make this little funny bow tie shape, we will be able to account for these different densities around this basketball-shaped head. Okay? So that's why we use that type of filter. The reason I'm talking to you is about talking you through that thinking is because I think it's helpful to understand how we can shape the X-ray beam. That's especially helpful for the therapy students to be thinking about how X-ray beams can be shaped. Not so much maybe for the nuke med people. We still do shaping of the X-ray beam in X-ray, but we do it digitally now. So we'll get into that some more. But the big way that we shape, the main filter that we might use in CT would be that bow tie filter. Collimation. Strictly speaking, the collimators restrict the X-ray beam to specific areas and they reduce scatter radiation. So they will improve image contrast by reducing scatter. Any reduction in scatter radiation results in improvement of contrast. That's true for X-ray, that's true for CT, just on down the line. Now, there is a type of collimation that then occurs after the remnant beam is exiting the patient. So when I say that about collimation, it reduces scatter, it improves contrast. I'm talking about collimation that happens on the tube side. There's also some collimation that happens after the X-rays are exiting the patient, and just kind of file that away in the back of your mind for right now and know that that's a separate kind of collimation. We'll talk about that later. So maybe the term for this, so we have source collimation, and they call, I think, pre-detector collimation. Our detectors, we use detectors to collect information, and a lot of times we use the terms interchangeably, but a detector is like a single detector element. And in our case, it's going to be a crystal. When we talk about the whole bank of detectors. The technical term for that is the detector array. So we have a detector array, and if you look at this illustration page, top of page 117, it's showing kind of a bank of things over here receiving the X-ray beams. That would be like a detector array. There's a bunch of different advantages for different detector materials, and it's something that is continuing to evolve. I would say that most of the evolutions in CT hardware have kind of culminated in the technology that we have now, and moving forward we're going to see more of an evolution in software and software design. So right now it's not, you don't need to know or memorize what detector elements we're using, other than to understand that it's a solid state crystal. Okay, so if you look at the bottom of page 117 or at 117, just go ahead and X out xenon gas. We don't do anything with xenon gas anymore. Don't even read it. It doesn't matter. I mean, it's helpful to have a historical perspective on it, but I'm not going to test you on anything related to xenon gas. It's everything's solid state crystal now. So looking at crystals at the bottom of page 18, there's a number of things we can say about these detector elements. They've been made from a variety of different materials. Some of them are materials that we might use in nuclear medicine. Some of them are materials that we might use in computed tomography or computed radiography. But things like cadmium tungstate, bismuth germanate, cesium iodide should probably sound familiar to some folks. And then certain ceramic rare earth things like gadolinium, which is used also as a nuclear medicine thing, and yttrium, which actually nuclear medicine uses, yttrium-90, I think, sometimes for therapeutic treatments and stuff. The thing that we like about these things, these compounds, is they have a high atomic number and a high density compared to things like xenon gas. So they're going to stop the X-rays and they're going to detect the X-ray. So it's kind of two different things that lead to what we would call a detective quantum efficiency, a DQE. They have a high DQE because they're able to stop the X-rays and detect the X-rays. And that's just like kind of over here, if you look at the top of page 118, it says solid state detectors have high absorption coefficients. They absorb nearly 100% of the photons that reach them. That's really, really great. We like that. Now, within the detector array, there's interspace material between each little tiny detector element, okay? And so that interspace material can actually form it can collimate the beam to some degree. It can almost function like a grid that we use in the X-ray systems. So we'll talk about that in just a minute. But just understand that the size of the detector element is called the aperture. And the smaller that detector is, the better the spatial resolution will be. So if you notice, I'm just at the bottom of that last paragraph on solid state crystals, and I'm literally reading right out of the book right now. These are important basic principles that we should understand about these detectors. That they can, the smaller these apertures are, the better the spatial resolution will be, and the better it will get rid of scatter. Basically almost functions like a grid in X-ray. Let's talk a little bit about, okay, so in here is kind of an overview of that CT scan hardware. Okay, I'm going to zoom in on this so no one lose your lunch or anything. This is an illustration towards, I think, the end of our chapter in the textbook. And yeah, on page 21. I really like this illustration because it walks us through every single aspect of data acquisition. Okay, so it begins with an X-ray tube. We have maybe some kind of filter. The source collimators, those move through the patient and isocenter of the gantry. They are going to be fan-shaped, and so we'll talk about why that's important when we talk about the history of these things. Then they will be incident on a detector array. That detector array is going to create an electric signal that is analog. That will be converted to a digital signal by the ADC, and that digital data is then what the computer uses to generate the image. That journey that I just kind of charted out for you, you need to be able to recite in your sleep. Okay? Hunter land trip. There you go. There you go. Data acquisition system. Okay, next to it we've got this illustration that I've given you. It's basically the same thing. I'm just showing you in a different format, right? So we have the same parts, but now we see how they relate. So I'm asking you, how do these things connect, and then where might they be placed? So if you want to take a stab, I'll give us a few minutes to think through that here at the end of the discussion. But it may be helpful to look between the two and see what you can figure out, what you can't, and label that to the best of your ability, just to kind of quiz yourself and use that as a way to quiz yourself on your understanding of this journey, as we will, of X-ray tube to data. I want to point out one thing, and I should temper this a little bit, but page 16, box 2.3, according to the current data, is wrong. Now, is this still controversial? Yes. But the big point here that I want to make is this is a point of significant confusion, especially for X-ray tech students. Okay? In the world of X-ray, increasing the KVP does what to patient dose? It will decrease your patient dose. Interesting, it's one of those weird flipped paradigms where increasing the X-ray power, it will actually decrease our patient dose. That's a good thing, right? We can still get the pictures we need without exposing the patients to a lot of needless radiation. CT is a little bit more complicated, is the short answer. It's using computers, it's using a huge array of software algorithms to do the image production that it does. And because of that, the increasing of KVP does not necessarily mean a decreased patient dose in CT. It's true for X-ray, not true for CT. Why not? Well, the current research indicates that further dose reduction can be achieved by just reducing the tube voltage. And that has to do with these software packages that we can tie it into. We can reduce the voltage, we can reduce KVP, and use the software to get rid of the noise. That's the short answer. We'll talk more about it when we talk about reconstruction. Okay? But this is, again, controversial. I will not be testing you on box 2.3. Just know that it is a controversial area. It is not that simple as it's presented there. Let's talk a little bit about these scanner generations. And the big thing here is we don't necessarily, if you notice just by the number of illustrations that she gives, we've got 3 illustrations of the 3rd generation and 1 illustration of the 4th, no illustrations of the 1st or 2nd generation. 1st and 2nd generation scanning just helps us understand how the technology evolved. But the big thing to understand about 1st is that it's defunct. We no longer use 1st generation scanning. It used a single beam of X-rays, almost like a pencil beam of X-ray, and a single detector. And they scanned across the patient, and then they reset, and they moved, and they scanned, and then they reset, and then they moved, and they scanned, and they reset. And you can imagine that took a long time, like upwards of 20 minutes to get a single slice. A long time. So 2nd generation was awesome in that it introduced a fan beam way of scanning. Now, there was one question out there, I think, in one of our online quizzes that said something about fan beam and where is it associated with. It was initially developed for 2nd generation scanning, but we continue to use fan beam. We like fan beam. So 1st generation gave us the algorithm that we use. 2nd generation gave us the fan beam. 3rd generation gave us the fan beam plus the slip ring. And it's the one that we love. Every CT scanner currently being manufactured is a 3rd generation CT scanner. And then everyone's like, well, wait, hold the phone. What's the deal with the 4th generation? The 4th generation is almost like that bad movie that you wish they'd never made, like that sequel that was like, oh, I liked the first one, but the sequel stunk, right? That's kind of the 4th generation CT scanner. It's more or less obsolete now, but the idea with it was let's line the entire gantry tube with detectors, and we can scan that much more quickly. It didn't turn out to be that advantageous. And the big thing that is helpful, I want to point out, in terms of technology, I think we've all got that the slip rings are awesome, fan beam is awesome, those things are good, those are awesome. I want to point out one little tiny thing here at the top of page 19 about this detector spacing and aperture, right? This is something that we could easily gloss over, but it's equally awesome. It's just as awesome as the slip rings and the fan beams and all that kind of stuff. This third generation allows for a certain amount of scatter acceptance beyond which it's not going to accept image-forming X-ray. So again, this aperture operates like a grid. It's going to filter out scatter. That's awesome, right? Because it will increase our image resolution that much better. It's one of those kind of hidden awesomenesses of third generation scanning. But again, the big takeaway here is test makers love these kind of trick questions, because it's kind of just ready-made for a trick question. What's the most currently produced scanner generation? Everyone's going to think, well, it's fourth, right? Because that's the newest one. No, it's third. Everything is third now. Let's talk a little bit about the patient table. And she doesn't quite give us enough on this. And let me hit pause for just a sec on patient table, and talk a little bit about these detector electronics. I've talked about it quite a bit already, but the big thing for us to understand about this detector electronics for this point in time is on page 20, where it says X-ray photons that strike the detector must be measured and converted to a digital signal to be sent to the computer to be analyzed. That process is going to be handled by a digital acquisition system, a DAS, and the primary part, the moving part that you need to understand most intimately is this analog to digital converter. Because what's coming off of the detector array is just an electronic signal. It's a bunch of ups and downs of an electronic signal. That is then digitized. And that's what the computer is going to use, is that digital data, ones and zeros, right? Binary code to construct an image. And we're talking about thousands of photon interactions per second. Thousands of photon interactions per second that it's converting, quantizing to digital information. So when we talk about big data, when we talk about image generation and the sheer volume of images that we're looking at, these things are doing a lot of work. Let's talk about the patient table, because it's probably the first place that you will have an opportunity to work with the CT scanner, right? I'll tell you what an old and wise tech told me my first day as a CT tech. I cross-trained into CT at the end of my senior year in X-ray tech school. So I had a very brief life as an X-ray tech, almost went immediately into CT, and that first day on the job I was very nervous because I had no clue what was going on. I knew that contrast could potentially kill you. I knew that all sorts of terrible stuff could happen, like air emboluses and stuff like that. I knew that I was going to be handling trauma patients and seeing all sorts of bloody messes and stuff. Like sometimes you would walk past the CT room door and it would just look like a horror show, right? Has anyone had that experience at any of the facilities you're at? Maybe not so much in outpatient imaging, but definitely in trauma imaging. There was days where the CT scanner would literally be covered in blood. It was pretty intense. That's not all the facilities you will work at, but that was the facility that I trained at. And that first day on the job, the tech told me there will be no births, deaths, or conceptions on this table, right? And that stayed with me to this day. That's a very good general rule of thumb for how to be a good CT tech. It's incredibly difficult to prevent those things. I can tell you from experience. I have not been guilty of the conceptions thing, but I have known techs who were. I have seen people die on a CT scanner. Fortunately, I've never seen someone born on a CT scanner. So the process of working with this table, I know you're looking at me like you're completely insane. The process of working at the reason I tell you all that is a lot happens on this table. So don't think that because she gives kind of short shrift to the table or whatever, it's not that important. It's super important, and we'll talk about how important it is right now. So the process of moving the table within the gantry we will call feed or step or index. And the more intimate you are understanding the numbers and stuff that are happening on the gantry as you move the table around, the better CT technologist you're going to be. Because you will have a more intimate understanding of how you're orienting yourself within this pile of data, right? So the degree to which the table can move in and out of the CT scanner, we're going to call the scannable range, and it should have somewhere on that table a mark that says you need to set your patients up below this mark. It's not, it can't go past this mark. The table also has weight limits. People will literally call your department and say, what is your weight limit on your table? Generally, it's best to lie about what your weight limit is by about 50 pounds. So if it's 400, I'm going to tell them it's 350. Why did I just lie? Because they probably lie too, right? If they're 400 pounds, they're going to tell me they're 350, right? So it's 350, wink, wink, because you're 350, right? The scan table also has this indexing system that's directly associated with it. So it has a separate computer that controls just the scan table, and it is tied to the data that you're getting during data acquisition. This is an important part of CT scanning, that we can tie the image data that we're getting to a specific spatial place on the patient. That's a powerful thing if you think about, like, especially for guiding surgeries or guiding stereotactic procedures or radiation therapy planning or interventional procedures, is I can say, okay, I know that this point in the patient's body is X number of millimeters superior to this point in the patient's body. That's really important. So, but zeroing out the table will probably be the very first thing that you learn how to do. There are, on most CT scanners, there's two different zeros, right? Why are there two different zeros? Well, one of them you can zero with the patient outside of the tube, and one of them you can zero with the patient inside the tube. So it's important to know which one zeros with them inside the tube and which one zeros with them outside the tube. They have little illegible hieroglyphics on the control panel to try to tell you that, right? But there's laser lights that converge on the patient. You can turn on the lasers, instruct the patient to close their eyes. I'm going to turn on some lasers, right? No one needs to be staring at lasers. You will then be able to see in 3 different directions where that ISO center is. So along the z-axis, along the y-axis, and along the x-axis, I can say the 0 point is right there. If I had a smoke machine, I could walk into the room and blow a lot of smoke in there and see right where all those lasers converge. That's what I'm lining up. I'm lining up the machine ISO center to the center of the patient. This is one of the most important things that you can do, and every tech acts like it's kind of just a ho-hum thing. But you can reduce patient dose by approximately 30% by just zeroing the CT scanner appropriately. That's not always possible, but it is something to consider. So, anatomic landmarks. The table readout will be set to some point called 0, and you will determine where that point is. And typical anatomic landmarks are like the xiphoid notch, or the sternal notch, the iliac crest, this kind of EAM, if you're setting up for a skull, external auditory meatus here. When you zero to that point, right, you will have a table range now from that point. So this point right there is 0. Everything like south of it will be negative whatever, and everything north of it will be positive. Now, I'm just generalizing here because every CT system's a little bit different on which way goes negative and which way goes positive. But it's very important to know that, because depending on if I set my 0 correctly, everything that the scanner does from that point on will be either correct or incorrect. It's almost like the foundation. That zeroing point is the foundation for the rest of the scan. So incorrect table referencing can produce artifacts and increase patient dose. Here's some of the research that I found on that. So failure to center the patient in the CT gantry isocenter can result in an increase in image noise and patient dose. Miscentering the patient by as little as 3 centimeters can increase surface dose by 18% and noise by 6%. And the short answer for that is that it actually has to do with a degradation in the performance of that bow tie filter. So the bow tie filter came back around like a boomerang, kind of hit us in the back of the head. If we're going to use this bow tie filter, we have to center appropriately, is the short answer. Here's my references, and thank y'all.